Hi, welcome to my continuing video series where I demonstrate projects that I've made that relate to computer graphics. This project relates to a ray tracer that I made. This both belongs to a project that was made for a class and to a project that I continued to work on after the class was finished. So it's kind of a combination of a class project and then an ongoing effort to improve upon the project that I started in the class. So in the class, when we implemented it, we actually did not implement it in this particular language or framework. The class requested that we make a ray tracer that renders with HTML canvas, basically, through whatever means possible. So in theory, we could try to write a script that we could call from JavaScript or whatever, and then display it in an HTML browser, basically. And that is what I did the first time I submitted the assignment. But then after I finished, I thought I wanted to try to implement it in a systems language and try to improve upon the ray tracer that I wrote for the class, which did not run very quickly. But it didn't have to matter for the class. We were graded on the results that we got, and they just were pretty generous with how long it took to render. Granted that they did request that it not take more than a hour or so to render, understandably. So sorry to take a sip of a drink. Here is so this is going to be different from my other videos. I'm first going to just briefly go over the code, and then I'll demonstrate what the ray tracer actually does. So I have updated this ray tracer actually more recently than this. I should probably add a new date to this, but I've improved it by first just rewriting it in a language that can compile the more performant assembly code than what something that is interpreted and run in a browser can do. So that's an immediate improvement already, just rewriting, just converting it over to a systems language. But on top of that, I made additional improvements that were related to algorithms, but also I implemented it to take advantage of multiple threads so that we can render different quadrants of the final image independently of each other in separate threads, and then combine the results once they have all the separate threads have finished running, and then display the results. And so how long it takes to render ends up taking a fourth the time, since I currently have a fixed number of threads. I could have written it to take any number of threads, and then in theory, if you have a system that has like a processor with, I don't know, 8 cores with each that has 2 threads, you could have 16 threads or whatever. But that seemed like a lot of work to have a scale like that would require that I be able to partition the image in ways that involved more work than I was willing to do. I just decided I wanted a fixed number of threads, 4, and that seemed good enough. So my code, I'm just going to scroll down through it, but basically it is written in Rust, the Rust programming language, which is a good language to use. I would recommend trying to learn Rust if you can. And I use some existing Rust libraries. One's called Piston, which is used for the windowing, and then I use a linear algebra library called NAlgebra for a lot of the matrix math and the vector math. And yeah, and I think those are the 2 external libraries that I use, other than like this timing library, which I use for debugging reasons. But beyond that, the rest is my code. So mostly what what ray tracing involves is conceptually you can imagine a plane that represents the window that is going to contain the final image, and you project view rays out from that window into an abstract environment, a world space basically, and you calculate those rays that are projected out from that window. You calculate those rays going out and hitting surfaces and bouncing around and stuff, and accumulating colors based off of what those light rays are essentially hitting. So in a certain sense, you're basically reversing the path of light from the light source to your eyes. You kind of flip that around and say, what if I could shoot rays out of my eyes. And then ultimately any rays that end up hitting a light source are ones that make color contributions to what I'm seeing, and then that ends up being the final image I make. It's a basically you kind of flip the roles of what's going on, and that's kind of what we end up doing. We cast out rays, but we treat well on some level there is everything has some ambient lighting component, so it doesn't have to hit a light source in my scene for it to make a color contribution. But if it does happen to result in it hitting a light, then it will be brighter because there are shadows in the scene, actually. Or rather, I take the inverse approach, and what I actually do is I project out from a light source shadow rays, actually. So, or any surface. Rather, what I do is I test any surface that hits any ray that hits a surface. We check whether or not there is a ray from that surface to the light source that is not occluded, rather. So, anyway. So that's kind of conceptually what we're doing with ray tracing, is we're basically just tracing the path that light takes as it bounces around a scene from your eye, so to speak, which ends up being a plane that represents the window, to surfaces and light sources and whatnot. And then you can kind of do things like reflections and kind of lighting and shading in interesting ways with this setup. So my render function mostly involves creating a window so let me, just looking at this code, I should probably explain, you want to create surfaces for the view rays to kind of interact with. So this scene that we're going to be looking at is going to involve a snowman with different color properties for each of the spheres in the snowman, represented by these materials that I created using a material type that I defined in Rust. And then I also have a mirror surface material, a floor material, and a brass color material for a cube that will also be in the scene. So basically the scene is going to be composed of a floor with a checkerboard pattern, a cube with a brass material on it, a snowman that consists of an RBG colored spheres with various reflectivity indices that you notice that is a material property here. And then there's like a light source, and that's basically it. It's pretty straightforward. And everything is, I then define some vertices that I then use to create. So this is a material type that I create. These vertices are going to be used in surface types that I then define. And I create an array of surfaces and immediately pack in to this array of surfaces of specific types. So I have a sphere surface type and a triangle surface type. In theory, I could have gotten creative and then made like a compound type where there's a cube that is composed of triangles and so forth, but I tried to keep things simple, and basically the primitives are spheres and triangles, basically. And then Rust is a very thread-safe language, and so what I ended up doing to make all these computations work in parallel is I created a shared reference to this array of surfaces that can be passed to the different threads. And because these threads are only reading the surfaces rather than modifying them or updating them, this is a safe thing to do, and Rust allows it. Rust is very concerned with the safety of things, especially when they exist in parallel. It's a language that's designed around having static runtime guarantees of the safety of the code that you write. And then I kind of create some little helper functions, define some constants here that kind of are used to create the basis vectors for calculating the view rays that are cast out from the view plane, which is the window, basically. So I define a lambda function, which kind of contains some information that's passed in, that is calculated from, we pass in some parameters from the command line that kind of inform where the camera is located at. So I basically construct a lambda function that I pass into each of the threads, which will then have the ability to then calculate these projected view rays relative to the eye, which the eye and the plane that the view rays are being cast out of. So this is kind of like a function that we kind of construct within the scope of the main thread and then pass to these concurrent threads to then calculate their respective view rays. And then I create these 4 threads, and then kind of like pass in all of the all the information that they need to render their little quadrant, including that lambda that calculates the view rays. And then I basically just join all the threads again. And by the time that this line finishes executing, in theory, we have all the color information for the window that we want. And what we will then do is create what's called a piston window, and then go through the window. And I do something to improve the image quality that I hadn't done in the first assignment here. So this is an improvement I made, where I do something called supersampling, which is basically where you render the image at a higher resolution than the ultimate resolution of the image in the window. So I render it at twice the resolution in each dimension, and then average the colors of 4 pixels to be 1 pixel, and then translate that into the final window image space, basically. So what you get is that you get an image that's more smooth and refined, because it's kind of taking the color contributions of multiple discrete pixels and kind of combine and average them into one. So it ends up being effectively looking anti-aliasing the image in a certain sense. Aliasing you can think of as being artifacting that results from discretely rendering a scene with view rays that are hitting surfaces in a space that isn't really continuous. And also, that's just not the way that light works. Light is informed by waves, which are continuous rather than discrete. Sorry, take another sip of my drink. So I go through, and then I kind of do all the color averaging to kind of do the super sampling here, and then we render the final image. And this is basically the core loop of the thread. Then we kind of have each of this thread render function, which is what each of the individual threads will do, where it will kind of iterate over its little image quadrant here, defined by its boundaries, and then we kind of generate our view ray using that lambda that we passed in, and we go through each pixel in the image quadrant, and basically just calculate the surfaces that we hit, and then we calculate the color for that view ray if it hits a surface, basically. Otherwise, we return what's called the background color. So in theory, if this view ray never hits any surface, which it can, then we just kind of return a background color. It could be black, it could be white. I use sky blue, and that's basically it. This calculate color function is a sneaky function because it's a recursive function that calls a series of other functions that involve a shadow ray calculation, a reflection function that is used to kind of calculate the reflection of the view ray if it happens to hit a reflective surface. And this calculate color function here, which is specific to each surface, changes depending on if you're hitting the surface you're hitting is a sphere, or if it is a planar surface, which is going to be the triangle. And the reason why it's different is because there are different ways of calculating the surface normal depending on if you're a sphere or if you're a plane, but also there's different ways of calculating if you intersect a surface depending on if you are a sphere or if you are a triangle. And the math for calculating the intersection of a triangle ends up being far more complicated than the math for calculating whether or not you intersect a sphere. In fact, spheres are actually super easy to calculate if a ray intersects it. Like the math is pretty straightforward. Triangles are more involved. At least they're more involved to do in a way that's efficient. And I'm not going to go over the details of that. Suffice it to say that there's a lot of different algorithms for it. The algorithm that I ended up implementing is probably not the ideal algorithm. I actually have a temporary implementation of a more efficient version that I haven't quite gotten to work that I'm trying to use. Right now I have a version that's good enough. It doesn't take too long to render. But I would like to ultimately use the improved version, because where most of the time that I spend rendering happens to belong to the function that involves the intersection with these triangles. If I could improve the performance of that function, it would really dramatically improve the performance of my ray tracer. So I would like to do that ultimately, because in theory I could actually have a real-time ray tracer, an interactive ray tracer that could render images in real time, and you could move the camera around the scene. Right now, it just renders the image and displays it, and that's it, and it kind of stops there. It's not very efficient, or I should say, it's not very involved. It just creates an image. It might even be able to do things in real time. Just it might not be ideal. It would probably not have a very high frame rate. It would be a bit on the low end, but it might be interactive. It might cause you to be nauseous, maybe. It's hard to say, but if I could improve that function, it could actually be something that could be interactive. My ray tracer. For now, it's kind of interactive. I could probably try to implement it that way and it'd be okay, but I think I prefer to first make an improvement to this function for the triangle surface type before I would try to make it a real-time ray tracer. And then, yeah, here's some materials and structures that I defined for my program. I have a material structure, an image quadrant, and different surfaces, and one that also represents a view ray, apparently. And so so I have a lot of complicated stuff in here that basically is just the mathematical machinery of how the ray tracer works. There is spheres and triangles, like I mentioned earlier, and the math for calculating the intersection of a sphere. Let me show you where that's at. Right here, this hit function, and this is it, right? See, not much. It's like 6 lines of code, maybe. I have something here that calculates the discriminant, it looks like. Do the dot product here because that makes sense. Quadratic function that I defined probably a bit later. Anyway, that might belong to the surface type, actually. And then I have a calculate color function. This is basically a recursive function because I believe that it will call calculate. It will call reflect if it is a reflective surface, which may call yet another calculate color function. So it's recursive up to a certain depth, which I define as a parameter that is passed in. I could have created a global variable or like some type of constant variable for this depth, which is something that I would consider doing for a future improvement to the algorithm. I kind of don't like to use global variables, but whatever. It's not, there's cases where they make a lot of sense to use. So yeah, this is basically the crux of the algorithm. Here's the algorithm I use to calculate the intersection with the view area with the triangle. It's quite verbose. This ultimately compiles the code that's a bit more performant than it looks, but it's still not ideal. And one other improvement that I could make to this ray tracer is that if I go back up to the render function, right down here, what I am doing is something that's not terribly efficient, but I am kind of iterating over the draw window and painting each pixel one by one. What I really ultimately should do is try to use OpenGL and basically take those image quadrants and just combine them and then add them into an image buffer, load that into as a texture into OpenGL, and basically render a quad texture to the window in OpenGL. It's a lot more efficient because it can be done with like your vector coprocessor and combining your CPU and your GPU. It'd be more effective. You could use there's a lot of advantages to doing it with buffers than kind of doing it with within a loop in the CPU and in a function. It's just not. This is less efficient than basically just buffering the image into like a texture and then just running an OpenGL quad, basically with the final image as a texture that where the texture that is literally just a square on the screen, basically. So it's a bizarre thing to do, but it would be a more efficient thing. It would be a way more efficient way to render the scene, and that would also be something that would make this a ray tracer that could probably be more interactive. Because that's another place where this isn't very efficient, is when I'm going this little loop here, and it could more efficiently super sample as well, because there's OpenGL. There are certain OpenGL. There's things that. There are certain switches and kind of like things that you can do with OpenGL that would basically effectively have it do the code that I'm doing in here without me having to write it out, actually. Like OpenGL can totally like average out. It would basically it might even decide to super sample just in the texture filtering process itself, basically. So anyway, so now that I've explained all of this, and this has been terribly exciting, I'm sure, just to hear me explain all this, I'm going to demo the ray tracer. So Here we get to see it run. Cargo run. We're going to run the release build of this. Might have to compile first. I believe I probably had the debug or non-release build called last time. Hopefully this doesn't take too long to render. This is, again, terribly exciting. I apologize. I could probably be more particular with my dependencies with my import, and that might reduce a lot of the things that I'm compiling here, because I'm not entirely sure if a lot of these things it's compiling are actually used. For example, there's like a true type font library in here somewhere that I noticed, WinAPI, a bunch of stuff here that probably is being carried along with my piston window import, and I could probably import. You can probably more exclusively import certain libraries without having to kind of inherit dependencies from things that may belong to features that you may not use. I could be wrong about this, but I suspect there's probably a way to make this compile quicker by being more specific with my imports. Yeesh. This is what it feels like to be a systems programmer. You're just waiting for things to compile a lot. Getting a nice little simulation of being a systems programmer. Finally, we're rendering my we're compiling my code finally. Boom. And there we go. So that, you'll notice, didn't take terribly long to run. Let's actually close this now and rerun it, and you'll notice it'll be a lot faster. So now it's really fast. So you heard me complain a lot about the performance in a certain sense, but ultimately, when we look at the render time, it looks like it took about half a second to render, which seems like it went up since I updated Piston to the latest version, because prior to updating Piston, it was taking about a tenth of a second to render. So that's actually a bit obnoxious, but that's fine. That could be the overhead of, again, that render algorithm. So anyway, here is the image. You'll notice we had this nice little checkerboard floor that is reflective. We have this mirror sphere, which is entirely reflective. We have this bronze cube that I was telling you about that does shadows, or everything does shadows. And the floor is reflective as well, you'll notice. This middle sphere is also reflective, so there is kind of going to be, you're seeing multiple bounces going around here. This is a very contrived demonstration of the ray tracing graphics features, obviously. So yeah, these shadows are very smooth. And the image is very smooth. It might be hard to tell in this video because of the way I'm recording it, but you can always clone this and run this in Rust. So I have this available as a Git repository, which I will probably include when I post this to my my blog. Yeah, these reflections look quite nice, and the shadows are quite nice as well. And this reflection seems like it works. And if you look inside the reflection, you can see that there's a reflection of the sphere in this snowman, and a reflection of the snowman in the sphere that's inside of the reflection of the snowman, and so forth. And there's a max depth to the bounces in this algorithm. I believe it's like 5 or 6 or so. It might be higher. And a nice thing that I can do with my algorithm, or I'm sorry, with my program, we're going to go to the release build of this and run it, but we can pass in parameters that basically tell it where we want the camera to be based off of kind of input, input position. So we have the x coordinate, which we are going to give a value of 4. The y value, which is the height, we are going to give a value of 4 for now, and then the z value, which is kind of like the depth of the image. There's 2 horizontal planes, x and z, and this is the one that that is opposite the camera, I think, in that default, the values that we gave it. But let's run this again with these new values. So this took us to a location that's subtly different than the last one. So here we're kind of getting a taller view of the scene. That's not too bad. Let's try shortening the X position to 2.5, the depth to 3.5, and we'll keep that height the same. And let's see where this takes us. So now we're right above the scene. We're between the face-off between the sphere and the snowman and the cube. And this looks interesting. It's a nice little view. Yeah, we got this reflection here. We got the shadow here. And we got the... Yeah, so this is kind of nifty. We can kind of pass in these different parameters. You're seeing a bit of like the specularity as well. I do bidirectional reflection distribution effect with a Phong shading with all the surfaces and the materials. So you'll see that there's kind of like a subtle kind of specular effect. My material model is a little bit broken, actually, I discovered. I was looking at it and I have been abusing the way that I use the ambient component and the diffuse component is incorrect. I've actually switched their roles in the render pipeline. So that's one of those things that I've been needing to go back and fix. But as it turns out, it doesn't actually change the final image that much because of the values that I was giving them were close to being the same anyway. But it would the final image would be a little bit more reflective if I were to actually kind of change to use them properly. And that's a thing that I want to go back in and fix as well. But it would only be slightly more reflective. Again, it's all just the values I'm using for the one were intended to be used in the other and vice versa. But those values were arbitrarily chosen to make the image look good anyway. So I could, in theory, modify those values to get the same image if I had when they were kind of used in their correct roles. So it wouldn't really... It's not like conceptually, it's actually not a huge problem. It's just that internally in the code, it really just irritates me to no end that I totally just kind of switch the roles in my head of what those components and of the material properties of the lighting incorrectly. Just drives me nuts to this day. And I'm in the middle of school right now, so it's one of those things where I could go in and fix it, but that would be a thing that that time could be better spent probably working on my next thing, you know. So I've demonstrated the ray tracer, and it really does seem like it renders quite quickly. Like I hit enter, and then the image comes up within a second or so, which is pretty fast. My original ray tracer was a lot slower. It would take about 5 minutes to render, I think, maybe even longer. It was written in JavaScript, and it was running in a browser. And this is an order of magnitude many orders of magnitude faster. So, and it looks better because I was doing even more things wrong with my original ray tracer that I managed to fix in the process of converting it into the code here. Like the problems that this code has are really quite minor compared to what the problems I was getting in my original implementation of the ray tracer. So, thanks for watching this video. You've seen my ray tracer now. I've kind of have some blog posts that kind of go into some certain amount of detail about it, but this is a walkthrough of it that I feel like I should probably do. I hope to maybe do some other computer graphics projects in the future that will be a bit more involved and interesting. I want to do things that involve shaders that like geometry shaders, perhaps, or in tessellation, kind of control shader, tessellation and stuff. You know, some more advanced features of things that you can do with your graphics card. Maybe some GPU compute related things would be kind of cool. I want to do things that involve curves and vector graphics as well, for like rendering of things like vectors and fonts and Bezier curves and that type of stuff. You know, stuff that's in different domains of computer graphics, not just stuff that's like interactive gaming and animation related stuff, but stuff that also kind of goes into domains that are more related to like image processing and kind of computer graphics in a more traditional sense. So we'll see what I end up doing. But thanks for watching this video.